Hey Vsauce, Annie here. Have you ever thought to yourself, what would happen if I held a piece of graphite the size of a football that was recently used by a nuclear reactor? Yes, I know. This might be your first time thinking about it, but the actual answer is a bit disturbing. After a few seconds, the top layer of your skin will start to severely burn, completely exposing your dermis layer and continuing to do so if you keep holding onto the graphite. In fact, the amount of ionizing radiation you would get from that little piece of graphite would be equivalent to about 4 million chest x-rays beaming at your hand. Yet on the night of April 26th, 1986, Chernobyl's frontline workers and firefighters were not fully aware of this factor, placing approximately 28 people with severe radiation burns all over the body for the first 3 months, which later led to death. But before discussing the devastation caused after this accident, it is vital to understand the function and nuclear chemistry within Reactor 4 of the Chernobyl plant. The RBMK-1000 reactor, Реактор большой мощности канальной, which roughly translates to high power channel reactor, was a Soviet reactor design that was responsible for the Chernobyl accident due to numerous mechanics, physics, and chemistry factors. Firstly, the structure of the reactor consists of pressurized tubes, the element-filled reactor core, concrete shielding, and 2 nearby 2,000-ton turbines connected to the pressurized tubes. In order to turn these turbines, natural common water was boiled by absorbing heat from fission reactions occurring within the reactor core. This, in result, created steam, which then moved through the pressurized tubes to the 2 turbines. The gained energy of the steam acted as an input force to turn these turbines, therefore generating electricity from kinetic energy. To reuse this boiled water, the steam is then condensed and returned to the bottom of the core to go through the process again. In fact, the reactor core was about 7 meters high and 12 meters in diameter, which is approximately the size of this house if looking at the side view. But that doesn't even include the concrete shielding and the reactor building itself. Now, you might be wondering, what's that fission reaction I mentioned, and what is the core even filled with? Well, before we do that, let's get one thing straight. The RBMK-1000 reactor has parameters that affect the rate of reactivity within its core. This means that the rate of reactivity can either be increased, aka moderated, or decreased, depending on several factors. We could start with the first vital parameter of the reactor, the fission reaction itself. The RBMK reactor uses uranium-235 fueled rods, which is enriched by 2% so that fission would be possible without using heavy water. In our previous diagram, it can be pointed out that these fuel rods surround the water, and for a purpose. As we already know, fission occurs when a neutron collides with an atom, which is our uranium. However, it is important to acknowledge that fission in this case can give 2 results. 15% of it produces new uranium-236 isotopes and some gamma rays, which are then absorbed by the water for boiling. This is due to radiative neutron capture, a reaction in which neutron is completely absorbed to create a compound uranium nucleus, thus emitting energy in the form of gamma rays. Yet the other 85% produces nuclear waste, mainly xenon and strontium, alongside 3 extra neutrons which collide with other uranium atoms to produce a chain reaction. It is easily understandable that fission increases reactivity within the core, but are there any breaks to the system? Well, of course, there are control rods made of boron, which essentially decrease the reaction. Boron is simply a natural neutron absorber. Yet initiating and reducing the reaction is not enough. We need the gas pedal to the system. This is where the moderator rods made out of graphite come into play. Moderator rods simply sustain and balance the rate of fission, if handled properly. Due to the fact that neutrons increase their speed each time a fission reaction occurs, the chance of the produced neutron colliding with the next uranium-235 atom decreases. As a result, a moderator is needed to increase or decrease the speed of the neutron to control the speed of the reaction. And the best element to do this is carbon. Not only do carbon atoms rarely absorb neutrons, they also change the neutron speed from approximately the speed of light to the speed of sound by the neutrons colliding with the carbon nuclei in order to create a continuous, stable fission reaction. Alert! This is important for later. It is vital to remember that when removing the control rods from the nuclear core to enhance reactivity, shorter graphite rods take its place and work with all the other ones available, thus increasing reactivity. Without the graphite rods, the water would be the displacement, which would not really enhance reactivity because water is considered to be a neutron absorber. Thus, this makes our control boron rods an effective brake for the system. Another two parameters that balance each other out during reactivity are the positive void coefficient, PVC for short, and the negative temperature coefficient, NTC for short. Just letting you know, voids simply describe the produced steam within the core. The PVC is a relation between the volume of voids and the rate of reactivity, since voids increase the number of free neutrons within the core, therefore enhancing the chance of fission chain reaction. Yet liquid water also acts as a moderator in this reactor design. Hence, the increase in voids will cause free neutrons to speed up, which in turn decreases the chance of fission. This now explains the NTC, where higher temperatures increase voids, thus stabilizing and decreasing the rate of reactivity. Lastly, the xenon waste created by 85% of the uranium fission is not actually stable, meaning that it also absorbs neutrons in order to stabilize. A sufficient amount of xenon may even quote-unquote kill the rate of reactivity by absorbing all available neutrons within the core. With so many well thought out and established parameters balancing the rate of reactivity within the core, it was simply impossible to get reactivity to the point of disaster. Or is it? At the time, the Soviet Union was striving to prove that their RBMK-1000 design was efficient and safe. So, on April 26, 1986, the operators planned to show that the kinetic energy in the spinning down turbines is indeed enough energy to provide for the emergency equipment within the reactor core. It was planned to drop the reactor's usual thermal energy of the core, 3,200 megawatts to 700 megawatts, but in reality, regulations state that holding the reactor below 700 megawatts is forbidden. Hence, an accidental slight decrease below the limit on site gave the operators a drastic drop to 30 megawatts, with numerous violations, which included leaving less than 8 control rods out of the total 211. The operators were able to increase the power to 200 megawatts, which was just enough to manually move steam through the reactor to turn the turbines and to continue the simulation. Yet the lack of control rods placed the remaining slow-flowing water into the position of being the only neutron absorber. Besides, a low flow meant that voids couldn't really be pushed through the pressurized channels with enough efficiency. This increase in voids then increased the PVC, which raised reactivity. More and more water was boiling away, and the AZ5 emergency switch was finally activated to insert all the control rods at once. Now, do you remember those graphite rods that I mentioned that displace the control rods upon removal? Well, since we already know that there isn't enough water at the top and the bottom of the core for neutron absorption, when the AZ5 inserted all the control rods at once, the graphite displaced all the water at the bottom of the core. The AZ5 activation was unfortunately too slow, since 18 seconds was enough to create an uncontrollable runaway reaction, where fuel rods were only surrounded by graphite rods, raising the pressure and the temperature above 3,000 degrees Celsius. The reactor's power was about 33,000 megawatts at this point, well above the limit. With such high temperatures, water steam, or voids, began to expand at an extreme rate as its molecules gained energy. It got to the point where water molecules have dissociated into hydrogen and oxygen gas, which essentially created a steam explosion. According to my calculations, the estimated pressure at that point would have been 40 megapascals, given that its normal pressure within the reactor core is 6.9 megapascals. And might I add, 1 megapascal equals to 1,000 kilopascals. The 40 megapascals has simply reached concrete's compressive strength to the point where the reactor shield could not hold it anymore. Thus, fuel, moderator, and control rods were broken into pieces, alongside the concrete lid being blown off to expose the reactor core, just like a heated balloon. But obviously much worse. Now, it is vital to acknowledge graphite, aka carbon. With the bulk form of this greasy-like element, the steel-gray graphite is not flammable. Yet it is known that graphite's melting point is 3,650 degrees Celsius, and the reactor heating up to that temperature sure made the carbon atoms heat up and disperse along with the water steam. I As a result, when dispersed particles of graphite were released into the air, the graphite and the oxygen reacted with each other and created severe combustion as they formed carbon dioxide. The exposed graphite fire required approximately 10 days to extinguish by dropping 5,000 tons of sand and lead material. Thus, radioactivity fumes and nuclear lava leaks surely had enough time to contaminate everything on their way. Great contributors to this radioactivity are xenon-144 and strontium-90, which are the products of uranium fission. After xenon decays to cesium-137 after 9.2 hours, both of the radioactive wastes are unstable and come to have a half-life of more than 30 years. This explains why Chernobyl's site is still harmful to this day. Yet most of this particular waste went into the atmosphere with the other products of graphite combustion, which was later transported by wind to a northeastern direction. This contaminated air mass spread through Belarus, Finland, Sweden, Poland, Czech Republic, Austria, Germany, Great Britain, and northeast France. After approximately 8 days, the wind direction changed to the east, and many Soviet populations, especially Moscow, also faced radiation exposure. The remaining radioactive wastes, like uranium-235, melted through the reactor shafts and mixed with sand, lead, and cement. Chemists call this matter corium, which essentially acted as lava, melting everything on its way. After about 10 days since the explosion, the melting mass of corium finally solidified, creating the infamous elephant's foot. Oh, and might I add, the electromagnetic spectrum, ionizing radiation, which can be seen right here, comes in the form of alpha and beta particles and gamma rays. And that, in very large doses, is very harmful to us. So, whoever was exposed to such radioactive waste after the Chernobyl accident might have suffered the risks of damaged tissues or mutations/alterations of one's DNA. As a result, there were more than 1,800 documented cases of thyroid cancer, which causes other cancers within the body, in children between the ages of 0 to 14 years old. On the other hand, adults were mostly affected on the psychological level, since suicide rates, addictions, and apathy increased dramatically. Additionally, many pregnant women were afraid of the risk of their future child getting serious abnormalities. Hence, this could explain the 30 to 60 abortions per day. Fortunately, that rate slowed down after a few weeks. After 36 hours, more than 200,000 people were evacuated and relocated from the exclusion zone, which has a radius of 30 kilometers from the Chernobyl plant. Radioactive contamination of aquifers and soil made it impossible for human life in such environment, yet it may have opened a safe haven for endangered species. Although many genetic mutations were present in Chernobyl's animal and plant species, natural selection has given the ability for these organisms to survive in a radioactive environment where the annual radiation dose is 5 times higher than the natural level at the present day. To avoid further contamination, an immediate construction project of a large concrete shelter over the reactor was initiated. Named Sarcophagus, it was built as quickly as possible, taking them only 6 months. However, this meant that the structure was at the risk of becoming weaker over the next coming decades. So, starting from the 1990s, the International Shelter Implementation Plan was launched. Operators, engineers, and nuclear chemists have collaborated to plan the construction of a huge new safe confinement structure in 2007. Using an arc formation, the 36,000-ton shelter was completed in 2017 using many materials, such as steel, cranes, and cladding. The plan also stated that the radioactive waste within the reactor core should be contained and removed to avoid environmental hazards. At the present day, they are beginning to do so remotely to make sure radiation affects as few workers as possible. Despite the devastation this accident caused across many populations, it has increased the collaboration between the East and the West. Better designs, experimentation, simulations, education, and projects can be seen today. Even international programs started to come up. For example, the World Association of Nuclear Operators and the International Atomic Energy Agency. With the help of international operators, chemists, and nuclear engineers working together in these programs, the repetition of the Chernobyl accident is now virtually impossible. Feel free to add any questions or concerns, and I'd love to hear any of your ideas. But as always,